Hey everybody, this is Scott, and today I have a video on full VM images in Docker. So a while ago I did a couple of videos about how to create both micro VM images and full VM images for use on the ThreeFold Grid. If you saw those videos, or if you're at all familiar with these concepts, you might remember that micro VM images are based on Docker containers, whereas full VM images were based on disk images. But wait, forget everything that you thought you knew about micro VMs and full VMs, because we have some new features on the grid that allow us to now work with full VMs in Docker. So in this video, I'm going to cover kind of what that's about, how to customize, build, and test images, and also talk a bit about why this is awesome. Basically, this is really cool because it allows us to use the workflows that we know and love in Docker to build full VM machine images, including things like custom kernels, or at least even just full kernels that include features that we might want to include in our VMs. And just to refresh on that, our micro VMs are booted with their own kernel, so they are VMs, but they get that kernel from 0S. The kernel that ships in 0S and is booted with the micro VMs is rather minimal. So if you're looking for certain things like being able to load kernel modules, you might not be able to do that in a micro VM. That's where full VMs are nice, because you can get that full-fledged kernel with modules, anything else. But typically that's meant moving to a full VM image. Those are just a bit tougher to work with and a bit less flexible than working with Docker images. So now we have full VMs that we can make in Docker. We don't have to. You could actually use other tools if you want, but in the end, what we get is just an archive that's got a file system inside, and that's what we provide to 0S. That file system includes a kernel and a init RAM disk. So this is cool for certain use cases, like on the grid we have WireGuard networks that your VM can belong to. But if you wanted to put kernel-based WireGuard inside of your VM to do your own solution, then that's something that might not work with a micro VM. And one use case in particular that I've been looking at is encrypting, doing full disk encryption using dmcrypt, which is kernel-based encryption. And that is also not going to work inside of micro VM. So we need the full VM, but I also wanted to be able to take advantage of Docker and customize these images and build solutions on top of them. So that's why I started playing with this after learning that it was possible from our developers. So our prereqs for today are going to be Docker, of course. We'll be using QEMU on the local machine to test our images before we ship them off to the grid. And then a ThreeFold Hub and Playground account is helpful if you actually want to test these images on the grid. It's not fully required. If you just want to build some images and run them in QEMU, you can totally do that on your local machine. One thing I'll say here is that QEMU is going to give us an idea about whether or not our images will run on the grid. It's not 100%. I'm still working on a setup that will provide a closer environment to what is happening inside of ZOS. ZOS is using Cloud Hypervisor, but the biggest thing is that ZOS is using a virt.io file system to serve the root file system. That's the case in micro VMs. So far, the full VMs, since they're based on disk images, they're using a disk image driver. But when we do this form of a full VM, we're also going to get a virt.io file system for the root file system. There's some caveats there, like if you want to run Docker on top of this, it's not going to work with the most performant Docker drivers. So again, if you want to use Docker, you should probably attach a disk, put your Docker data root on that disk, and just know that these root file systems, virt.io FS, are not going to be the most performant. So again, if you need high performance, attach a disk. But other than that, these full VMs are kind of what you would be used to in terms of, in this case, we'll have systemd inside of our VM, and we can put any software in there that we want as well. So for now, I'm hosting the Docker files and scripts that make possible what you see in the video today on my own personal repo. This is at github.com, Scott Yeager, TF Images. Once I've got these in a nice place and find a nice home for them, we'll get them into some ThreeFold repos. But for now, if you want to check it out, it's here on GitHub. There's some instructions here that you can read through. We'll cover all this in the video today. So let's head over. So I'll just pretend that I've cloned this repo, and now I am here, in particular inside the full VM folder. So inside the TF Images, you'll find full VM. And here we have 4 scripts and 2 folders in the README. So these folders are what contain the Docker files that are used to build the images, and then the scripts are used for building and testing the images. So right now I have a minimal Ubuntu image, which is based on KVM kernel, which is really small. It's built for VMs, so it doesn't have much like hardware drivers and things that you would need in a full system. The crypt, Ubuntu crypt, is where I'm working on Ubuntu with the encrypted disks. I won't show that off today. That'll come in a later video. Today I just want to show the full VM and Docker functionality. So if we look inside Ubuntu minimal, so far there's a Docker file and there's also a tar archive. That tar archive actually doesn't come with the what you would clone from GitHub. So let's just go ahead and remove that and get ourselves into a fresh state here. So Ubuntu minimal, we just have a Docker file, and this is what you will get when you clone the repo. So let's take a look inside of this Docker file. It's a bit large and might look kind of complicated. This is definitely not your typical Docker file. We have several stages. 1, 2, I think there's 4 stages altogether, and we'll explain why that is. And we are doing some things that you don't normally do in Docker files because we need this image to be a standalone image rather than an image that runs in Docker. And there's some things that Docker will do for us that we're not going to get when we boot this up on its own inside of the hypervisor. So let's just go through this image kind of at a high level from the top. So in the beginning, we're starting with an Ubuntu container. This will pull Ubuntu latest. That's fine. We're just using this one as our bootstrap. So in this case, we're going to download our package lists and just install the deb bootstrap program. We're going to make a rootfs folder, and then we're going to run deb bootstrap. We're going to take the min base variant, which is basically the smallest version of Ubuntu or Debian that deb bootstrap will install. We're going to get the jammy version of Ubuntu from archive.ubuntu.com, and we're going to place that into the rootfs. So when we use deb bootstrap, this is going to create a fresh root file system that's fully populated with all of the basic things that we need to use our Ubuntu system, like the app package manager and some utilities. And typically, if you're looking at how to use deb bootstrap, the next thing that we would do is change root into this new root file system that we've created. Instead, we're going to do something sort of equivalent in Docker. We're going to start with a new image from scratch. This is just a blank image. And what we're going to do is copy in from our bootstrap image the root file system into the root of our new image. So that freshly bootstrapped Ubuntu system will now be sitting at the root of our new container, which we're calling image. And this is where we'll do most of the sort of creation of this image. And this is the part that is kind of like what you would do in a normal Docker file. We're also going to pull in the sources list from an Ubuntu Jammy container. So when we do deb bootstrap, it's going to give us a very minimal sources list with just one or two of the repos. And some of the packages that I want to install are from other lists like Extra or Universe or whatever. So when we copy in this sources list from the container image, that will give us everything that we need. And so this always needs to match this jammy here and this jammy here. Maybe in a future version of this file, this would be like an argument or something that you could pass in if you wanted to build different versions, but that's a bit more complicated because we also have a kernel version, which we can see here. So this is the kernel that I'm going to build with Ubuntu. There's normally a few versions that you can get at any point in time. 5.15 is the most prevalent one. There's also 5.19, which I discovered when I was doing the encrypted image because 5.19 happens to work well, whereas 5.15 does not for some things I was trying to do there. But whatever your kernel is here, you're going to write it there and it'll be used in a couple places below as we are installing and extracting the kernel. We'll talk about that later. Again, KVM is nice because it is a minimal kernel designed for virtualized environments, but it doesn't have a lot of modules. It actually doesn't have the dmcrypt module that I was looking for the full disk encryption, but it's a nice place to start for a minimal install. If you want more modules and more stuff, we can switch to the generic, which I think is 2.5 generic, and you can look up the different kernels that are available in different versions of Ubuntu and pick the one that you want. All right, so now here inside of our bootstrapped Ubuntu system, we're going to run some commands. This here is a heredoc form of the docker run command, which basically just turns everything below here into a script, which is nice. We don't have to write run every time or do a bunch of double ampersands to chain these commands together. We're going to install some packages. I'm always using no recommends because I like to keep my images lean, but that's up to you if you want to install recommended packages. Sometimes you'll find that you actually want to have them. Okay, we're going to install CloudInit. CloudInit is what will be responsible for setting up the users, the networking inside of our system. CloudInit's got a lot of features. We don't use a ton of them on the grid, but it's how the SSH authorized keys are injected into the VM, how it gets its host name, and how it gets its networking information. I'm also going to install OpenSSH so that we can connect to this VM over SSH. We'll grab curl for downloading file later. By installing this Linux modules package, this depends on the Linux kernel image, so that's going to pull in the kernel as well when we install this, so we'll get the modules and the kernel. We're going to download the initramfs tools that we'll use to rebuild our initramfs, and we'll grab binutils. We need inside binutils the readelf utility that's going to be used by the kernel extraction script we'll see later. And then we have a few more packages here. LSB release, locales. These are used, locales are used by CloudInit, and LSB release is, I think, also used by CloudInit. Finally, this libpam systemd. This is important for systemd and system control. There's some other packages around systemd that we're not installing. There might be some things you find that are missing. In this setup, I basically just installed the minimal set of packages I could find to get a working system. I've done some tests with it, but you might find there's some things lacking in here. But at least you can boot this up, you can SSH into it, and you can install whatever you need from there. Also adding less, this is just something that I like to have inside of all my VMs. I tend to miss it if it's not there. So again, we're trying to stay pretty lean. I'm not installing any editors or anything crazy. Next, we are going to regenerate the init RAM FS with the fsvert.io FS module included. So this is needed because, again, like I was saying earlier, the root file system that ZOS is going to attach to our VM will be a vert.io FS. So in order for the system to boot, the init RAM-FS needs to include this driver so that it can mount that file system and change root over. That's just some details, but the important thing to know is that you need this if you want your system to boot. So leave it there, and here we're updating. That's going to rebuild the init RAM-FS. Next, we're going to extract the kernel. So when ZOS boots this form of flist, and flist is what we convert the archives that we'll get out of this process into. Flist is our native format on the grid for packing and shipping groups of files. So when ZOS opens up this flist and looks inside, it's going to see that we have a kernel and we have an init RAM-FS. So it's going to do what's called a direct kernel boot using a cloud hypervisor, which is built into ZOS. And when we do the direct kernel boot, we need an extracted kernel. Kernels typically are compressed. That's what the Z here on the end of VM Linux stands for, is compressed. So we're going to decompress the kernel using a script that comes out of the Linux kernel GitHub. This is the script. You just download it. We're going to run it. We're going to extract the kernel to a version with elf at the end. This is just an intermediate step because we can't extract and overwrite the same thing at the same time. But basically, we just overwrite the compressed kernel with an uncompressed kernel, and then we're going to remove the script. I mean, leave it behind. It might be useful later if you wanted to update the kernel in your VM. That's one thing to keep in mind. This VM is not going to get any automatic kernel updates because we have specified the kernel version up here when we installed it. There are packages that you can install in Ubuntu, and like a normal cloud image or a server image is going to get a kernel package that results in automatic updates. We're not going to do that here because any update to the kernel would break the system on reboot if it was not extracted. So maybe someday in the future we'll have like some hooks that we can add to apt ourselves or something like this that would allow automatic kernel updates to work and extract them automatically. But for now, the thing to know is that if you want to update the kernel in a VM like this, you should do so carefully. Be sure to extract the new kernel and probably test it outside of your production environment first, as always. All right, so at the end here, I'm going to remove bin utils because we no longer need readelf after we did this. Bin utils isn't a huge package, but again, just trying to keep things lean here. It has a few dependencies, so we'll also remove those. And then we're just going to clean up the apt cache and get rid of the package list. This is kind of standard procedure for Docker containers to keep them light. It doesn't necessarily hurt to have these lists in there, but normally the first thing you do when you start up a new VM is update the list anyway, so we won't ship those in our image. All right, so that's the whole image build here, and a lot of this is just taking care of stuff that we need to do to make this image work inside of the environment it's going to run in. We have some cleanup at the bottom, and pretty much anywhere in here you could place your own customizations. If you want to add packages, you can just append them onto the list here. If you need to run any other commands inside of this script, it doesn't super matter where you put them, but this might be the best place just in case you happen to do something that affects the init ramfs, but even so, it should generally rebuild itself. So yeah, I would put your commands in here for anything that you want to do. If you want to copy files into this VM or anything like that, you can do that with the standard Docker file directives. Just put them outside of this block. And that's it. So basically in here we have our kind of normal Docker thing that we can do our normal Docker stuff. We can install custom software. We can insert config files. We can even do things like set up systemd services. There's some limits to what we can do with systemd inside of Docker because we're not actually going to start these containers with systemd inside of Docker. That's technically possible, especially if you're using Podman, I guess, but I haven't tested it. So that's another thing maybe I'll play with more later and see if we can actually get more of this workflow in the container tools. But at some point, you're going to want to hand it over to QEMU to run it as a VM anyway. And that's going to be the most reliable way to make sure that whatever you're doing works when you go to launch it on the grid. So that's our second stage, Bootstrap, and then this is the image stage. And the final stage I'm calling touch-up, and this is where we do a couple things that we can't do to this image while it's actually the kind of current running image inside of Docker. So this would be like dropping out of our change root if we were using change root instead of Docker. So here we'd be dropping out of the change root and maybe doing a couple final cleanup steps. So here what we're going to do is we're going to copy the entire root file system from the image step, and we're going to put it again into a rootfs folder inside of an Ubuntu container. And this case, we don't really need Ubuntu. This could be anything else. We just need a few standard Linux utilities, but hey, we're Ubuntu all the way, so why not? So we're going to copy the image that we just made into a folder called rootfs here. And then we're going to remove resolve.conf. This would be either an empty file or whatever was placed there by Docker. I think Docker is bind mounting or placing resolve.conf inside the container for us. So once we remove this, we'll replace it with a symbolic link to our systemd resolve.conf because we want systemd to be managing our DNS servers. And the way these symlinks work can be a bit of a mind bender, but the way I like to think about this is whatever is on the left is what the path that the link will resolve to when this is in its final state, and then on the right we have the destination inside of our current paradigm where rootfs is the root there. Anyway, this works, and if you want to confuse yourself, try playing around with it. That's, again, going to be there because Docker is taking care of resolve.conf when we run a Docker container. And this piece here is writing in a host file. So Docker, again, is going to have its own host file, and this is one that I've just copied essentially from the Ubuntu installer. So this is just kind of standard boilerplate stuff, localhost and IPv6. I think Cloud Init might do something with this when we boot up, or maybe not, but I found that if I didn't put this in, I had some issues, so this is good to have. And then our final step, we're going to use tar to package up this root file system into a compressed tar archive called img. And then finally, we have one more phase, stage in our build. And this is really just here so that we can generate an empty container and put this archive inside of it. This is just due to some kind of quirks around how Docker works. We can't actually just copy this archive out of our final phase here. The only thing that we can do is dump the contents of an entire build stage. So we just need to make an empty stage again from scratch. We're going to copy from this touch-up stage into the root only the archive. And we'll see what happens with that in just a moment. So that's the Docker file. And if you are wanting to do something custom here, again, you really only need to worry about this middle part and the first stage and the last two stages here. You shouldn't need really to ever edit those in order to do kind of customizations inside of your image, unless you're wanting, of course, to modify the host file or do something different with resolve.conf. You can do that here. If you wanted to try bootstrapping a non-minimalized version, I actually tried that and I didn't have success. The bootstrap is it works in Docker now, but it didn't before, so that's a more recent thing. It didn't seem to like trying to install the full setup. But I think once you have a min-based bootstrap, you should also be able to maybe say in this step, specify a wider group of packages and essentially get to kind of more of a standard install. There's some other stuff I was reading about how to call deb bootstrap with like a fake change root or something. Anyway, if you know anything about that, let me know. I found min-based to be the most reliable. It's nice and small. You can add the software that you want. If you want to try to bootstrap a full, the default install, you can also try that. Again, let me know how it goes. All right, so let's drop out of that and take a look at how we build this. So to build it, we'll call build.shell. Before we run build.shell, let's see what's inside. So this is a nice small shell script. This is a bit awkward unless let's just, nice and small, let's just cat it. Okay, so when we call build.shell, we're going to give it the name of one of these folders where there's a Docker file inside. So this first part is just going to take that, whatever we pass in, and if it has like a trailing slash, we're going to strip that off so we can get a nice name to use for our package. And then we're going to change directory into that path. This phase, Docker build x build with the output. So this is going to run through the full Docker file, and at that last stage, it's going to dump out the contents, which is just that tar archive, image.tar.gz, into the present folder. And then we're just going to rename that to be whatever the name is. So like we saw earlier inside Ubuntu Minimal, I had Ubuntu Minimal.tar.gz. And this last step here is also going to leave us with a Docker image that will be the build stage called image. So we're targeting the image phase, and we're going to tag that with the name. So this is going to give us two things in the end. One is a compressed tar archive that has the contents of that image target step with the touch-ups that we did in the end. And then we're also going to have a Docker image that contains the results of that image phase. And this is nice because we can start that image up with a shell. We can look around, see what's going on. This can help us to work on some issues that might come up. And it can also be a way to further customize images and quickly test them without needing to rewrite the Docker file and rerun the whole thing. So I'll show you how to do that because that's also pretty cool. One thing to know about this, though, is that these images can be kind of large, so you might want to check these out. You can feel free to remove them from your system if you're using these scripts, but it's there in case we want to play with it. So we'll run build.shell, and we'll run that on the minimal Ubuntu image just to see what it does. Probably this is going to go pretty fast because everything is cached, so don't expect it to work so quickly, but since I've already built this image, most stuff is coming from cache. But this is basically what it does. It just builds the image, and then it also tags the Docker image for us. So let's see what we got. Now we can see that this tar.gz is here. So that's cool. And then I can also look at Docker images and just look at the top. Oops, top couple images here. That's what I've been working on already. Yeah, so here's our Ubuntu minimal image, and then here's the encrypted jammy image I'm also working on. And stay tuned for more info on that. Here we can see, this image is about 400 megabytes, which is really not bad for a full VM image. The compressed version is about 130 megabytes, which is cool. But again, if you're working with a lot of these, it can eat up some disk space. So just keep an eye on that. Now, let's go ahead and run the test on this image. So again, if I look in here, I have the build script. I have a test script. Before I run test script, I need to generate a seed image, which is a small image file that just contains like our SSH key and some metadata about the machine. So if I run seed.shell, what it's going to do is look inside of my system for an SSH key under the home directory, .ssh, ID RSA or ID ed, whatever. And it's just going to insert that into the file here. So this has now written our image, seed.image, and these are the contents. So this is just like a generic name for the image, and we're going to have a root user, and the root user is going to have this SSH public key as an authorized key, so I can connect via SSH. Now, if I run test.shell, so test.shell takes in the path to an archive that contains an image, and I'm going to go ahead and run it, and then I'm going to talk about what it's doing, because this will take a minute. So what this script does is it creates a disk image from our tar archive. So again, when we use this image on the ThreeFold Grid, we don't need a disk image, but for the case of running it here inside of QEMU, this is the most convenient way to do it. So we're just going to dump those contents into a disk image, and then we're going to boot it up with QEMU, also with that seed image attached. So this assumes that you have the seed file there in the same folder. If you don't, your VM will still boot, I think, or maybe you'll get an error, but Cloud Init is not going to work, and then you're not going to be able to connect to your VM. So make sure you have the seed image before you run test. So yeah, the test script is just taking that tar archive, it's dumping it into an image, and then it's booting up the image. So every time we run the test script, it's going to generate a new image. And if you want to do something like boot the same image multiple times, you'll need to do something else. The test script doesn't support that. But if you look in there, you'll find a QEMU call that you can adapt to your own purposes. So here's Cloud Init setting up our VM. It's giving it an address. This is coming from QEMU's kind of default networking thing, which is really convenient. It gives you a DHCP server that the VM can grab an IP from, and It's all set up very nicely. We could take a look. So, in here, this is my SSH key going into authorized keys. So once we've come this far, we should be able to connect with SSH. Let's take just a quick look inside of the test script. So here's the part where it's building the images. There's some sudo stuff going on in here. So this is required to mount the image as a loopback device. I recommend that you read and understand the script before executing it with sudo. I've been using it quite a bit and it hasn't ruined my system yet. So yeah, use with caution. Everything else that I'm showing can be done without sudo, but this part I didn't find a way to do it without. We also have to extract the archive with sudo to preserve the file ownership. It's kind of a nice thing about working in Docker is that it takes care of this, but for this test phase, we'll need to use some sudo. And here's the QEMU call down here. It's pretty simple. We're doing, again, direct kernel boot. We're giving the init RAM disk. This is the image that it's generating, image.qcow, which is QEMU copy on write. We have our seed file there. We are telling the kernel which disk is our root disk. And this is the networking part. And what I wanted to show here is that we're mapping port 2222 on the local system to 22 inside the VM, which means that we can very easily SSH this VM by just SSHing to port 2222 on localhost, which is very convenient for our testing purposes. There's some more things I could say about this part, but let's take a look inside of our VM. To connect, just SSH, give port 2222, root at localhost. Anyway, don't mind that. Let's go ahead, we'll accept the host keys. And here we have our Ubuntu VM. We can see what's going on in here. We have systemd, SSH. We're using about 45 megs of RAM, which is, again, pretty good for a full VM. And we can do things like system control status, and it will show us that our system has been started up with systemd. And here we can try whatever we want, install software, etc. But again, this is a disposable test instance. So if you wanted to make any customizations to your system, don't do them in here. This is just for testing that your image works and that you're able to SSH to it, which is the most important bit. Actually, let's reconnect just quickly and look at one more thing, which is the block devices here. So if I do ls block, I'll see we have a VDA and a VDB. This is not quite how this VM is going to look on the grid. So this is one thing I wanted to tweak about the test script. Maybe I'll do that later. I wanted to set this up so we have the root as an SDA, and then our VDA would be, this is our seed image, and then it will look like it does on the grid. And if we added more disks, those will, on the grid, there'll be VDA, VDB, and then the last one, VDCD, whatever, would always be our seed image. It's kind of a small detail, but just something to know if you're trying to do anything that targets these block devices. VDA here is our root on the grid. VDA is not root. It's going to be the first disk. So this can be kind of a gotcha, but maybe in a future version of the script, we'll set this to be like an SDA or something. Just set it to a different type of virtual device, or even get the VirtIO FS working so that we can have a kind of complete test and also test for some of the gotchas that might come up when you are finally deploying this image to the grid. Ask me how I know that there are gotchas. All right. So let's now do one thing that I mentioned before, which I think is cool. We can't we can't use like Control C or anything to kill this. We just have to close the browser or the shell tab. As far as I know, there's no better. I guess we could do like a pkill QEMU. I just like to close those tabs up. So, and if we look at what happened here, now we have this temp folder, and that's just got our kernel, our netram disk, and our root file system image. Every time you run test, it's going to clear out this temp folder, so don't store your data in there and run the script, or you'll be sad. This is just a place to hold disposable files for testing. All right, so like I mentioned before, we can use our Docker image. So I'm going to go ahead and run in a remove. We'll do an auto remove here. You might not, we'll go ahead and remove that. So if you want to play around in an image and then export that to be a VM, you might not want to automatically remove it, but I like to add that so I don't get a lot of clutter. So here's our Docker image that we generated earlier. So this is from the image stage of our multi-stage build. And in here we have our root file system. If we look under boot, we have our kernel. We can try to run like system control. It's going to tell us that the system has not been booted with systemd, but we can do things like try is enabled, cloud-init, and that's true. So we can actually enable and maybe even disable services in here. So we can do some stuff with systemd even though it's not running, and we can customize our image. So if I want to install some software in here, I'll have to download the package list because we removed those, and I could do something very simple as an example, like install Vim, and now what I'll do is grab the hash of this container, which I see here. I can also grab that from Docker PS. That's going to be the container ID here. I'm going to run the freeze script that we also have, handy dandy freeze script. Freeze is going to take in the container ID. If we gave this container a name, or we could use the name here as well, and it's going to convert that into an archive that we can also boot as a VM. So this is pretty neat because now we can fire up our container. We can play around. We can apt-get. We can make files, delete files. We can do our systemd stuff, whatever we want. And in the end, we can just freeze that container, and then we can run it as a VM. So now I've got an image.tar here, and I can just use test again, test.shell on image.tar, and that's going to, again, clear out everything that was in temp. It's going to make a disk image out of this tar archive that we just froze from our running container, and now we can boot that up. It's going to do the full thing with cloud-init and all that. I won't bore you with watching all the details there. But this is cool because now I can have an interactive terminal here where I am playing with and customizing this image as I go. I can freeze those changes at any point, boot them up inside the VM, and see how they turn out. I don't necessarily recommend building your images this way. It would be better to figure out what works and then put that inside your Docker file and build it that way. That's going to be the cleanest thing, of course. But this can be a way for testing changes in a fast and convenient way. So over here, cloud-init is still doing its thing. Don't want to wait all day on it, but I was hoping to show you that we do indeed have Vim inside of our VM now. That should take just another minute or two. Open a new browser or a new terminal here for SSH while we're waiting on that. I can show you what's happening inside the freeze script. It's essentially just doing the touch-up and the last from scratch steps from the Docker file we had before. Just writing this Docker file into a temp folder. We are committing an image from a running container, doing a little bit of hackery here, using the image hash also as a tag for the image, and then at the end we remove it so everything is nice and clean. So this script was fun to write. If you're curious, have a look inside. I think by now we should be in a place here where we can do this. So I wonder if I can now SSH. Now we're inside here, and we have Vim. Yay. Okay. If you have a clue how to use Vim, then you'll be happy. Or put Nano in there, or Emacs, or whatever floats your boat. Okay, so let's go ahead and disconnect. I'm going to close out my VM and my test container. So that's showing you now how we can start to play around, experiment, customize, make sure that those actually boot up as VMs. The last thing I want to show is what you do with these archives in order to run them on the grid. I'm not going to give the full demo because it takes some time, but I'll just give you the outline of what you're going to do here. So I'm going to go to hub.grid.tf. So once I'm logged into the hub, I can hit this button, upload my file. I click here. I can then choose a file from my local disk and hit upload. That'll take a minute. It'll upload, extract. Once that's done, you can click this link to see the list of all flists that you've uploaded. In this case, I've been calling these flists some different things, but you'll want to come here and copy the link address for the flist, or if we open the flist, then we can also hit copy here. That will give us the link for the flist. And then in the playground, the confusing thing is that we actually use the workflow to deploy a micro VM in order to deploy our full VM flist. So that again is a bit confusing, but that's the way that it works for now. Probably will update things in the future so that that is more clear. But as far as the playground is concerned, this is more like a micro VM than a full VM. And we could now choose a farm and deploy this flist as a VM if we wanted to. Because I'm not going to show that part now. That would be sort of boring. We'll just watch it deploy and connect again via SSH. So I'll leave that up to you. Try for yourself. If everything went well, your image should be a working full VM image that you can run on the ThreeFold Grid. All right, so that has been full VM images in Docker. I hope that you found this video helpful and inspiring. I hope you go try building some full VM images in Docker. Feel free, as always, to connect with me if you have any questions or want to share something cool that you built. I would love to hear from you. Again, all the code that I showed off today is on GitHub, my own personal TF Images repo for now, but coming soon to ThreeFold repositories. And that's all for today. See you later.